Hello children, continuation of exercise 11.3. Fifth question, find the Cartesian and vector equation of the plane that passes through the point 1, 0, minus 2 and normal to the plane I plus j minus k. It's given A is I minus 2k and n is I plus j minus k. Equation of the plane passing through the point whose position vector is A and normal to the plane is n, which is r minus a dot n equal to 0. So we can write this as r minus a is I minus 2k dot I plus j minus k, which is equal to 0, which is r dot I plus j minus k minus I minus 2k dot I plus j minus k, which is equal to 0, which is r dot I plus j minus k minus of I dot I is 1 minus 2k into minus k, which is plus 2, which is equal to 0. R dot I plus j minus k minus 3, which is equal to 0, which is the required equation of the plane in vector form. Now we have to find in Cartesian form. Put r equal to xi plus yj plus zk in the equation of the plane. We get xi plus yj plus zk dot I plus j minus k minus 3, which is equal to 0. So simplifying this, we get x plus y minus z minus 3, which is equal to 0, which is the required Cartesian form of the plane. Sixth question, find the equation of the plane that passes through 3 points 1, 1, minus 1, 6, 4, minus 5, minus 4, minus 2, 3. So we know that the equation of the plane passes through the 3 points are x1, y1, z1, x2, y2, z2 and x3, y3, z3, which is determinant of x minus x1, y minus y1, z minus z1, x2 minus x1, y2 minus y1, z2 minus z1, x3 minus x1, y3 minus y1, z3 minus z1, which is equal to 0. Here x1, y1, z1 is y1, 1 and minus 1 respectively. Then x2, y2, z2 is 6, 4, minus 5, x3, y3, z3 is minus 4, minus 2 and 3. Equation of the plane is x minus 1, y minus 1, z plus 1, x2 minus x1 is 6 minus 1, 4 minus 1, minus 5 plus 1, minus 4 minus 1, minus 2 minus 1, 3 plus 1, which is equal to 0, which is x minus 1, y minus 1, z plus 1, 5, 3 and minus 4, minus 5, minus 3 and plus 4, which is equal to 0. Expanding along the first row, we get x minus 1 into 12 minus 12. Then minus of y minus 1 into 20 minus 20 plus z plus 1 into minus 15 and plus 15, which is equal to 0. So we get x minus 1 into 0 minus y minus 1 into 0 and z plus 1 into 0, which is 0 equal to 0. Hence we say that the given points are collinear. Hence there will be infinite number of plane that passes through the given points. Intercept form of the equation of a plane. In this section we shall deduce the equation of a plane in terms of the intercepts made by the plane on the coordinate axis. Let the equation of the plane be ax plus by plus cz plus d equal to 0, where d is not equal to 0. Let the plane make intercepts a, b, c on x, y and z axis respectively. Hence the plane meets x, y and z axis at a 0, 0, 0b0 and 0, 0, c respectively. Therefore, A into A plus D, which is equal to 0, or we can write this as A equal to minus D by A. And again B into B plus D equal to 0, or B equal to minus D by B. Then C plus D equal to 0. So C equal to minus D by C. Substituting these values in equation of the plane, we get minus D by A minus D by BY minus D by CZ plus D equal to 0. Minus of X by A, we take D as common, plus Y by B plus Z by C, which is equal to minus D. So cancelling negative and D, we get 1, which is X by A plus Y by B plus Z by C, which is equal to 1, which is the required equation of the plane in intercept form. Exercise 11.3, 7th question. Find the intercepts cut off by the plane 2x plus y minus z, which is equal to 5. We know that the intercept of the plane is x by a plus y by b plus z by c, which is equal to 1. And given plane is 2x plus y minus z, which is equal to 5. Dividing the whole equation by 5, we get 2 by 5 of x plus 1 by 5 of y minus 1 by 5 of z, which is equal to 1. We can write this equation as x by 5 by 2 plus y by 5 minus z by 5. Otherwise, we can write this as plus of z by minus 5, which is equal to 1. So comparing these two equations, we have a equal to 5 by 2, b equal to 5 and c equal to minus 5. Hence, the required intercepts are 5 by 2, 5, minus 5. 8th question. Find the equation of the plane with intercept 3 on the y-axis and parallel to ZOX plane. Given that the required plane is parallel to ZOX plane and has intercept 3 on y-axis, that is b equal to 3. We know the intercept form of the plane is x by a plus y by b plus z by c, which is equal to 1. Here we have x by 0, a and c are 0. So x by 0 plus y by 3 plus z by 0, which is equal to 1, which implies that y equal to 3. Plane passing through the intersection of two given planes. Let pi 1 and pi 2 be two planes with equations r dot n1 which is equal to d1 and r dot n2 which is equal to d2 respectively. The position vector of any point on the line of intersection must satisfy both the equations. Let t is the position vector of a point on the line. Then this can be written as t dot n1 which is equal to d1 and t dot n2 which is equal to d2. Therefore, for all real values lambda, we have t dot n1 plus lambda of n2 which is equal to d1 plus lambda of d2. Since t is arbitrary, it satisfies for any point on the line. Hence, the equation r dot n1 plus lambda of n2 which is equal to d1 plus lambda of d2. Hence, the equation r dot n1 plus lambda of n2 which is equal to d1 plus lambda of d2, which represents a plane pi 3, which is such that if any vector r satisfies both the equations pi 1 and pi 2, it also satisfies the equation pi 3. Any plane passing through the intersection of the planes r dot n1 equal to d1 and r dot n2 equal to d2 has the equation r dot n1 plus lambda of n2 which is equal to d1 plus lambda of d2. So Cartesian form is n1 is a1i plus b2j plus c3k, n2 is a2i plus b2j plus c3k, and r is xi plus yj plus zk. Then this equation will become x into a1 plus lambda of a2 plus y into b1 plus lambda of b2 plus z into c1 plus lambda of c2, which is equal to d1 plus lambda of d2. Or we can write this as a1x plus b1y plus c1z minus d1 plus lambda of a2x plus b2y plus c2z minus d2, which is equal to 0, which is the required Cartesian form of the equation of the plane passing through the intersection of the given planes for each value of lambda. Ninth question, find the equation of the plane through the intersection of the planes 3x minus y plus 2z minus 4 equal to 0 and x plus y plus z minus 2 equal to 0 and the point 2, 2, 1. Equation of the two planes are given by 3x minus y plus 2z minus 4 equal to 0. We can take this as 1 and x plus y plus z minus 2 equal to 0. We can take this equation as 2. So equation of any plane passing through the line of intersection of the given planes 1 and 2, we get 3x minus y plus 2z minus 4 plus lambda of x plus y plus z minus 2, which is equal to 0. So using the formula a1x plus b1y plus c1z minus d1 plus lambda of a2x plus b2y plus c2z minus d2, which is equal to 0. We can write this equation as 3 plus lambda of x plus minus 1 plus lambda of y plus 2 plus lambda of z minus 4 minus 2 lambda, which is equal to 0. If the plane is passing through the point 2, 2, 1. Substituting these points in this equation, we get 3 plus lambda of 2 plus minus 1 plus lambda of 2 plus 2 plus lambda of 1 minus 4 minus 2 lambda, which is equal to 0. So we get 6 plus 2 lambda minus 2 plus 2 lambda plus 2 into 1 2 plus lambda minus 4 minus 2 lambda, which is equal to 0. We have 2, 4, 5 lambda minus 2 lambda, which is 3 lambda. Then 6 minus 2, 4, 4 plus 2, 6, 6 minus 4, 2. So 2 plus 3 lambda, which is equal to 0, 3 lambda equal to minus 2. So we get lambda equal to minus 2 by 3. Substituting the value of lambda in the equation of the plane, we get 3x minus y plus 2z minus 4 minus 2 by 3 of x plus y plus z minus 2, which is equal to 0. So we get 3 into 3, 9x minus 3y plus 6z minus 12 minus 2x minus 2y minus 2z plus 4, which is equal to 0. So simplifying this, 9x minus 2x, which is 7x, minus 3y and minus 2y minus 5y plus 6z minus 2z is 4z, minus 12 and plus 4 minus 8, which is equal to 0. So required equation of the plane is 7x minus 5y plus 4z minus 8, which is equal to 0. Coplanarity of two lines. Let the given lines be r equal to a1 plus lambda into b1. We take this equation as 1. And r equal to a2 plus lambda into b2. We take this equation as 2. The line 1, which passes through the point say A with position vector a1, which is parallel to b1. And the line 2. This line 2, which passes through the point say B with position vector a2, which is parallel to b2. Then AB equal to A2 minus A1. The given lines are coplanar if and only if AB is perpendicular to B1 cross B2. Therefore, AB dot B1 cross B2, which is equal to 0. Or we can write this as A2 minus A1 dot B1 cross B2, which is equal to 0. Writing this in Cartesian form, let A with coordinates x1, y1, z1 and B with coordinates x2, y2, z2. We have AB, A2 minus A1. So x2 minus x1 of I plus y2 minus y1 of j plus z2 minus z1 of k. And B1 is A1i plus B1j plus C1k and B2 is A2i plus B2j plus C2k. The given lines are coplanar if and only if AB dot B1 cross B2, which is equal to 0. Writing this in determinant form, x2 minus x1, y2 minus y1, z2 minus z1, a1, b1, c1, a2, b2, c2, which is equal to 0. Distance of a point from a plane, vector form. Consider a point P with position vector A and a plane pi 1 whose equation is r dot n equal to d. Consider a plane pi 2 3p parallel to the plane pi 1. The unit vector normal to pi 2 is n cap. Hence its equation is r minus a dot n, which is equal to 0. So this we can write it as r dot n, which is equal to a dot n. The distance ON dash of this plane from the origin is a dot n. Therefore, the distance PQ from the plane pi 1 is ON minus ON dash. So that we can get NN dash, ON minus ON dash, which is D minus A dot N, which is the length of the perpendicular from a point to the given plane. Hence, distance of the plane is D minus A dot. If the equation of the plane pi 2 is in the form of R dot N, which is equal to D, where N is normal to the plane, then the perpendicular distance, which is A dot N minus D by modulus of N. Length of the perpendicular from the origin to the plane R dot N, which is D by modulus of N bar, since A is equal to 0. So writing this in Cartesian form, let P be x1, y1, z1 be the given point with position vector A and ax plus by plus cz equal to D. The Cartesian equation of the given plane, then A is x1i plus y1j plus z1k and n is aa plus bj plus ck. The perpendicular from P to the plane is x1i plus y1j plus z1k dot aa plus bj plus ck minus D whole upon root of a square plus b square plus c square, which is modulus of ax1 plus by1 plus cz1 minus d whole divided by root of a square plus b square plus c square. Exercise 11.3, 14th one. Find the distance of each of the given points from the corresponding given planes. So point is 0, 0, 0 and the plane is given as 3x minus 4y plus 12z, which is equal to 0. We know that distance of a point x1, y1, z1, the point is x1, y1, z1, from a plane ax plus by plus cz, which is equal to d, is modulus of ax1 plus by1 plus cz1 minus d whole upon root of a square plus b square plus c square. The point is 0, 0, 0 and the plane is given as 3x minus 4y plus 12z, which is equal to 3, which is equal to 3 into 0. The point x1, y1, z1 are 0, 0, 0. 3 into 0 minus 4 into 0 plus 12 into 0 whole divided by 3 square plus minus 4 whole square plus 12 whole square. And minus d is minus 3 which is equal to minus 3 by 9 plus 16 plus 144. So root of 9 plus 16 plus 144, which is equal to 3 by root 169, which is 3 by 13 units. Second subdivision, the point x1, y1, z1 are 3, minus 2 and 1. And the plane given as 2x minus y plus 2z plus 3 equal to 0. So using this formula, modulus of ax1 plus by1 plus cz1 minus d divided by root of a square plus b square plus c square. The plane is 2x minus y plus 2z plus 3. Point is 3 minus 2, 1. So 2 into 3 minus 1 into minus 2 plus 2 into 1 plus 3 divided by root of 2 square plus minus 1 whole square plus 2 square, which is 6 plus 2 plus 2 plus 3 divided by root of 4 plus 1 plus 4, which is equal to 13 by root 9, which is 13 by 3 units. Thank you, children.